Hello. Today I will continue our first lecture on underlying thoughts of calculus. At last class, at last lecture, I explained uh, the derivatives. Okay, and I defined derivative. Just for review, uh, derivative. The mathematical definition of derivatives is this one: limit delta x tends to 0, delta y by delta x. Okay, and mathematical notation of derivative is dy by dx. Okay, uh, but this derivative is very important. Uh, uh, is important in science and everywhere, of course. It has its different meaning at different sciences, branches of sciences. Suppose mathematically this is defined by this formula, okay, and we denote it dy by dx. But geometrically this is in fact slopes. That is, if we have a function y equal to f of x, and derivative mean that is at any point x, the slope of the function or slope of the tangent lines. Okay, so if our function is curvilinear, so at every point slopes will be different. Okay, so this is our derivative. So geometrically derivative means slopes of curve. Okay, and but physical theme is rate of change, that is which is in fact instantaneous rate of change of the function. Okay, so and economic theme is marginal concept. Okay, marginal concept, and it has its humanistic approach, which is in fact we can say this is reflection or sensitiveness of one variable to another variable, যেটাকে আমরা বলতে পারি আসলে আমজনতার যে কনসেপ্ট, না, that is everywhere we use this derivative. That is, we every time in fact encounter two types of variables where one variable reflect on another variable. So we are nowhere without derivative. So we have to interpret the concept of derivative at different sciences. Okay, whether this is biological or physical science or economic science, okay, or any other sciences. So this underlying idea is very important. So now I want to focus on roots of calculus. In fact, that is the origin problems that push to invent or to discovery of calculus. That is, in fact, calculus, this is a Greek word which means calculation. But our Greek ancient mathematician, famous mathematician Archimedes, started in fact calculation of area of circle, rectangle, squares, or volume of pyramids. Okay, but in fact modern calculus started its journey by discovery of fundamental principles of calculus, which is in fact by English scientist Newton, okay, Isaac Newton, and German scientist Gottfried Leibniz. Okay, at the second half of 17th century. Right? Okay, four major originated problems that push the discovery of calculus. These problems were the tangent line problems for a general curve. How to find the slopes at every point, okay, of a function. That is, in fact, how to find rate of change function. In fact, rate of changes, that is instantaneous rate of changes. Okay, second question was area. How to find area of a general region, or volume of a general solid, or length of a general curve. Okay, third problem was how to maximize or minimize of a quantity function. Okay, and fourth problem was how to find velocity v of t or acceleration function a of t if given suppose some distance function, okay, s of t position function, or converse, okay, if given velocity function or acceleration function, how to find the position function or distance formula. Okay, so these four mathematical major problems push the calculus to invent, in fact. Okay, discovery of calculus, in fact, what is the discovery of calculus? Calculus discovered the fundamental relationship between tangent line problems and area area problems. Okay, that is which is tangent line problems, that is how to find the slopes. Okay, and area problems, that is this is in fact original function. In fact, physical theme, if we consider physical theme, that is tangent line problems or slopes problems, this is instantaneous rate of change function. Okay, instantaneous rate of change. Okay, but what about the area problem or area function? This is in fact how to find the original function. If given rate of change function, how to find original function. So relationship between rate of change function and the original function in absolute volume, okay, or in absolute quantity. So this relationship, this is a fundamental relationship. Okay, or mathematically we say this is a derivative function. Okay, tangent line problems, that is derivative function, and original function, which is in fact antiderivative function, is if given a derivative function, how to find antiderivative function, or if given antiderivative function or original function, how to find derivative function. Okay, so relationship between these two parts. Okay, so for example, if for differentiation, if we have a function y equal to f of x, okay, this is in fact an original function, or for example, this is f of t. This is an COVID infected function people. Okay, COVID infected people, that is quantity of people. No? Okay, and if we want to find the infection rate, in that case we have to differentiate the COVID function. Okay, ddx or ddt. Okay, so with respect to x, if we differentiate f of x function, or with respect to t, we will differentiate f of t function, and we will get in fact f prime of t, which is infection rate function. Okay, and conversely, when given rate of change function, suppose infection rate given is this one, our rate of change function, যেটাকে আমরা আসলে f of x দিয়ে সব সময় বুঝাই। হ্যাঁ, so given any function আমরা সেটাকে denote করি always by small f of x. Okay, but এটা আমরা জানি this function is rate of change function. So if we integrate the rate of change function, okay, here small f of x, which is rate of change function in fact, and we we integrate a rate of change function, that is infection rate function. Okay, we will get the original infected function. Okay, affected people. Okay, so in fact geometrically this is given a rate of change function y equal to small f of x, we integrate the rate of change function, we get an area function. This one is our area function a of x. Okay, area function, which is in fact our original function, or we say antiderivative function f of x. Okay, antiderivative function capital F of x. Okay, if we differentiate the area function or antiderivative function, whatever we say, we will get, you see by arrow, we will get the rate of change function. That is, this is the fundamental relationship between area function or antiderivative function to with rate of change function f of x. That is, if we differentiate capital F of x, we will get rate of change function small f of x. Okay, or if we integrate the small f of x, that is our rate of change function, we will get the antiderivative function or original function. This is in fact the crucial understanding or discovery of calculus, that is fundamental relationship. So this is all whatever I wanted to say. Thank you.